Let's start with a brief recap on planning. We motivated planning due to the problems with feedback control. First, if you have a behavior like this where collision avoidance is combined with goal-directed behavior, the forces that you compute and the resulting wheel movements can cancel each other out and the robot would get stuck in this U obstacle. But you also don't know whether the route is Let's start with a brief recap on planning. We motivated planning with the problems that feedback control has when driving the robot to a goal. For example, when you have a behavior that avoids collisions and drives toward a goal, like this star here, you might run into a scenario where the two forces, if you want, cancel out and the robot is stuck. So for example, in a new obstacle like this, then you need planning to actually move around and out of it. But you also don't know whether the resulting routes are the shortest. For example, if there's an obstacle here and the robot turns this way, then it might get stuck here and this route would have been shorter, which you would have found out only with planning. Finally, we need planning because we do want to know when the robot actually is done with something, when it arrives. Otherwise, the controller is not very useful. We then developed the A-star algorithm by starting from breadth first search, which is the way to guarantee optimality. When a breadth first search algorithm finds the goal for the first time, you know that you also found the shortest path. When you have non-uniform edge cost, like for example these diagonals which are longer than one here, or even more complicated non-uniform edge cost, you have to use a min-heap approach to implement BFS, and you can then add a heuristic to direct the exploration toward the goal, which leads to A-star. We also talked about graph traversal. We initially started using a graph where you essentially move from one node to its neighbors via the edges, but then also looked at algorithms to generate these neighborhoods from grids. In that case, we use some function like getNeighbors, where you provide a node or a coordinate on a grid, and in return you get valid neighboring coordinates. For this, we essentially loop through a list of delta-like motions, so I can go to the right, I can go to the left, I can up, or I can go down, and then we tried all these different directions out. This is a very general approach. If you have a chessboard and a knight, then you might use moves that only the knight can do, which is moving 2 in one direction and 1 to the side. But it works actually for any discrete search problem like this 15 puzzle, where you want to move these tiles to reorder the tiles 1, 2, 3 to 15. And what you can do is you can use a 16-dimensional vector where each entry is the number of the current tile and 0 is for the empty one. And you can then look at a configuration and generate possible moves. Like in this case, the 7 can move down and the 13 can move to the left, and generate neighboring nodes that way. And also here you can use an algorithm like A-star to find the solution. A heuristic here could, for example, be the number of tiles that are in the wrong location, or it could be the sum of all the errors in the Manhattan distance for every single tile. So this tile has an error of 1, this tile has an error of 1, and this tile would need to be down here, so it's an error of 4, and so on. Now, this is important because we want to talk more about limitations of grid-based approaches in high-dimensional spaces. This space is actually quite limited because you don't have all the possible combinations, but only those that you can actually reach by moving those tiles around. But if you have a robotic car or even a robotic arm, maybe one with 2 arms, a robot with 2 arms, you very quickly get very high dimensions. Now, we also talked about a multi-layer architecture to planning, where we have the feedback control approach at the bottom, and at the top level we would use graph-based search. And then we have already seen this picture here, where the search doesn't happen on a grid, but actually in the continuous space of the road. And this is what we're going to be talking about today. It's called sampling-based planning. So when you search on a grid, the first problem is obviously you have to still do quite a lot of exploration. Now you see where the goal is, it's over here, and you see how slowly this breadth-first search approach is growing, this disk if you want. And if you add another dimension here, you would have to grow a sphere, which has a lot more points to search than a disk. And if it's 4-dimensional, you would have a 4D sphere, and so on. Now, if you have a robot like this, it's a 12-dimensional search space to find configurations like this. Now, searching this using a grid-based approach will take quite some time. Now, you can always decrease the resolution, of course, but then the question is, what is the resolution that you really need? And at the one extreme, you're wasting a lot of time searching all these very small cells. At the other extreme, you are not finding the solution because your resolution is not big enough. So all of these things are motivations for using a sampling-based approach, where you can actually use continuous values. And this works as follows. Instead of discretizing the configuration space into a grid, we simply sample from continuous coordinates. That is, we would throw a dice to get the position and the orientation in continuous double values, if you want, instead of integers. When we have a robot arm which has 6 joints, we essentially throw 6 dice to get 6 random numbers for each orientation, and so on. If you have a car like this, you might not only consider the position of where the car is, but also its velocity and acceleration. So every point here is not just a position, but it's also a position and a velocity, because I might be at the same position driving faster, slower. I might brake and I might accelerate at every point. So all of this can be done in multiple dimensions, where a sampling-based approach will be advantageous. Now, all we need is a function to generate those possible neighbors, and we can throw dices, we can reason about the data structure that we have, like in that puzzle, but we can also use a simulator to generate possible points in the configuration space by essentially simulating the car driving with small changes in the steering wheel or small accelerations and brakes. The way this looks like is like that. This is a rapidly exploring random tree. You see, once it finds the goal, it uses A* to find the shortest path. So the tree is really only used to explore this configuration space, using much less samples than if you would search the entire grid. But of course, what we get is not the optimal result. In this course, we will stop searching here. In practice, you wouldn't stop the RRT algorithm here. You would actually keep searching and improving this path. And once you are done with a path from the randomized planner, you would actually use another algorithm to optimize the trajectory by straightening it out. This is also something we will not do in this course. Alright, so here's how the basic algorithm works. As an input, we have a configuration space, which is an n-dimensional search space, and every point in this space is a suitable configuration for the robot. Here in this case, we are using a 2D map. You have a start node, Q start, and a goal that you want to get to, Q goal. Both of them are in the configuration space. You have some obstacles in it that the robot is not able to reach or be in. You have to provide the maximal number of vertices that you actually want to explore. So let's say I want to stop at 2000 possible configurations, And finally, you need a parameter delta q, which is the incremental distance with which you want to build the tree. Now, if this distance is too large, you will always hit obstacles. If it's too small, the algorithm would be too slow, so this is a tuning parameter. And what you get in return is a graph G that you can use to search for paths. So the first step is to initialize the graph with only one node, which is the start node, and then sample a random point in the configuration space. So in this case, you can literally throw a dart onto this configuration space. The dart lands here. You get two values, and this is my qrand. Now I have to find the nearest point that I already know in the graph. So I have to search the entire graph to find the point that has the lowest Euclidean distance, in this case, to the graph. In this case, that is the start node, that is the closest one. And now the parameter delta q comes in. I don't just add that qrand to the graph, but I move delta q into the direction of it. So I have a circle around the nearest node in the graph, which is here. And now I move along the direction to my random point, and I stop at delta q. So I call this new point q new, and now I check if this edge between the q near, the nearest one in the graph, and the new one is collision free. I add it, otherwise I drop it. Now I also check whether this point q new is close enough to q goal so that I can call it quits. In this case, that is not the case. So I keep doing that until I have k nodes. So again, I sample a random point qrand. I find the nearest point in the graph. Now this time it is this one, which is q near. And then I move delta q into the direction of qrand, and I get my new q near. Again, I check that for collisions. I barely made it here, and I can add this edge to the graph. Now the third iteration, again, I draw a random point, I put it down, I find the nearest point, which is q near, again this one. I move by delta q toward qrand, and I'm growing my graph. Now you might wonder, how do you ever get to the goal? Of course, you can grow there in every direction, like here and there, and eventually you will arrive at the goal. But there's a better way. I can actually set my random point to be the goal, and I want to do this every 10 or every 20 runs. So with probability p, 5% or 10%, I set qrand to be q goal. Now let's try that out. Now qrand is here. I find the nearest node in the graph, which is this one, and then I move delta q in its direction. Of course, if you do that all the time, the robot will quickly run into this obstacle, so you have to balance what is called exploration and exploitation. Exploitation being taking advantage of the information that you know, exploration being expanding what you know. Now this is how this looks like when you add some bias. You quickly move toward the goal. Now I found it, and then I run my A-star algorithm to find the shortest path. Alright, this was a very, very basic algorithm. There are thousands of papers on how to improve it, and I want to give you two improvements here that are important. The first one is called RT star, and the idea is that the paths could be more directed from the get-go if instead of adding q new to q near, which is the nearest one, I should actually add an edge to the node that is closest in the direction of the start node. So in this case, instead of adding this edge, I'm adding that edge and creating a tree in which most of the branches are pointing toward the start node. That means I have much less sharp turns, and when I then start the robot at the start node, I can probably very quickly drive to my goal and do not have to straighten the path as much. Now RRT star has a lot of more improvements on actually refining the graph and fixing it as the search progresses, which we don't want to cover here, just the basic idea. Here's how it looks like. I now show you all the edges that I would have added, and then I actually add the edge that is more directly going to the start node. So you see that here. So instead of adding this edge, I'm adding the edge that goes to the start node, and so on. And as the video progresses, you see that you have a tree that is really pointing toward the start node from everywhere in the environment. All right, another improvement is called C Forest, and is by one of my PhD students, Michael Otter. And this is about refining the T graph faster and even parallelizing the search. And the idea is that once a path is found, the space in which better paths can be found is bound by an ellipse, which you can get by essentially treating the path that you found as a rubber band, putting a pencil into it, and then creating an ellipse that goes around the start and the goal as the centers of the ellipse. And now I know that every point outside of this ellipse will not lead to a shorter path, and I can limit my search to being within the ellipse. And this is of course particularly interesting when I have multiple computers or multi-cores in a CPU trying to improve a path, and then all of the other CPUs can limit their search to the ellipsoid of the currently shortest path. All right, what we haven't done so far is collision checking. I have done the collision checking implicit in the grid-based search because we only explore neighbors that are free. With RRT, you quickly might end up running through an obstacle, so you have to do collision checking afterwards. And when you are in 2D or on a grid, this is essentially a line that you can search. We talked about Bresenham's line algorithm in the past. The algorithm also exists in multiple dimensions. So if you want to add a node to the graph, you will need to draw a line between where you're currently at, or the Q near node, and the Q next. You have to connect the two, and then you have to check every point along the line. Now this becomes quite cumbersome if you have a more complex robot like the Tiago robot, which also has an arm and a body and a head and all sorts of things, and you have a complex environment that you want to check against, like a table. Now how do you do that? In practice, this is nowadays done using computer graphics engines like Bullet or the Open Dynamics engine, which has built-in collision checking. So all you have to do is you have to load up a 3D model like in Webots, which is actually written in ODE. So a lot of the things that you are familiar with in Webots are directly accessing the ODE API, like the translation and rotation nodes and the entire tree structure. And you can therefore also very easily export a so-called universal robot descriptor file from Webots by right-clicking on your robot. And what you get is a file that looks like this, an XML file. Here I just show a small sample about the Hokuyu node that is in there. And you see it has a translation where it is on the robot and other geometric information. And you can then visualize that URDF file. And for the Tiago robot, you get this, which you see is not entirely what we have in Webots, but it is actually suitable for collision avoidance. Now you can use this 3D model and do pairwise testing with it and all the objects in the environment that are close by, and ask the graphics engine as to whether there is a collision. This is how this looks like. I implemented RT in PyBullet, and whenever I want to add a node to the graph, I put the robot down there, actually really move it there in PyBullet, and then I ask the engine, does this robot or this model collide with any of these objects that I have here? And if that is the case, then I do not add the node to the graph. Instead, I show it here as a yellow ball and add a red edge, which shows that this is an edge that I didn't add because of the collision. So you see here the goal is that yellow square, and the algorithm is eventually finding it. This is another example where you also see the limitations of the RT algorithm. The shortest path unfortunately doesn't work because the robot would cut the corner here. So I can't take that shortest path, and unfortunately it doesn't find that there is indeed a shortest path down here. So instead it goes all the way around, and now we find this initial path, which is actually very far from the optimal one, and you would need to keep searching in order to find a better path. Alright, in summary, the grid-based search approaches are infeasible in higher dimensions, and what you want to do is you want to sample the search space to make it more tractable. For that you can use randomized approaches such as rapidly exploring random trees, which enable fast exploration of large search spaces. This is also something we call sampling, and the collision checking is usually included with the sampling approach. So you sample first and then you check for collisions. This has been the opposite in the grid-based planning, where you first generate the C-space with all the obstacles therein, which is also computationally expensive. We then talked about how to do collision checking using computer graphics engines. There is an implementation of this linked from the course materials, so you can use that in PyBullet. And the final point is A star on the graph then remains the primary option for finding a shortest path on such a graph structure.